Good day. For those of you who don't know me, my name is Douglas Harder, and in this topic we're going to look at numerically approximating the derivative and using Richardson extrapolation. So in this topic we're going to discuss the use of interpolation to approximate the derivative. We will then look at the center divide difference approximation of the derivative and the second derivative, and in each case we will determine the error using Taylor series. Then we will look at the backwards divide difference approximation of the derivative, and again we'll look at the error analysis, and finally we'll use Richardson extrapolation. So by the end of this lab you will understand how to approximate first and second derivatives numerically. You will understand how Taylor series are used to determine errors of various approximations. You will know how to eliminate higher order errors using Richardson extrapolation, and you will have programmed a routine in MATLAB that approximates these terms with appropriate exception handling. So suppose we want to approximate the derivative. Now this is the formula you saw in first year for approximating the derivative. Now what this says is that if h is very small, then in the limit it equals the derivative. But if we use just a fixed value of h as small, then it should still be true that if we just use, say, h is equal to 0.001, we should get a reasonably close approximation of the derivative. Unfortunately, this isn't as easy as it seems. Let's say, for example, we want to differentiate sine at 1. Now, sine at 1 is cos at 1, but let's approximate it anyway. So we have sine of 1 plus h minus sine of 1 all over h. That is the formula you learned in first year. We will let h equal 10 to the negative I, where I runs from 0 to 20. So basically we will use the formula you saw in first year with values of h equaling 1, a tenth, a hundredth, and so on. Well, initially things seem to get better. As h gets smaller by a factor of 10, it seems that we get one more digit of accuracy with every single step. And again, there is the correct answer, cosine. So far so good. Unfortunately, after a while, the approximations get worse. As h gets smaller, we get fewer and fewer digits of accuracy until here, when h equals 10 to the negative 15, we get 10 to the negative 15, we get 0 as our approximation. Not a very good approximation. At least, well, it's 100% relative error. All right, so there's two things that must be explained here. Why is it that, to start with, we seem to be getting one more digit of accuracy with every single iteration, and then at some other point we seem to be losing a digit of accuracy with every single step? Ultimately we get a completely useless approximation. So why is this? Well, let's start with Taylor series. Now, Taylor series are one of the tools that we use in numeric approximations. So here we have u at x plus h is equal to u at x plus the derivative times h plus the second derivative evaluated at some point xi over 2 times h squared, and xi is somewhere in the interval from x to x plus h. So it's somewhere very, very close to x if h is small. What we're going to do now is solve for the derivative. We'll isolate that term, and now having isolated, we can divide both sides by h. Now, taking a look at this formula, we get that the derivative is equal to the formula, but on top of this, it also gives us the error term. It gives us an error term that tells us how close our approximation is to the actual value of the derivative. And again, xi here is some value of x, some value in the interval x to x plus h. Now, assuming that the second derivative is not varying too wildly, that means it doesn't grow arbitrarily large in a very small region, then we can actually sort of approximate that by a constant. So we can say that the derivative is equal to our approximation minus a small error, and that small error can be approximated by the derivative at the point x as opposed to the derivative at x at xi, where xi is somewhere between x and x plus h. Let's just use the second derivative at x. So thus we have our absolute error. The absolute error of our approximation is therefore approximately equal to m times h, and therefore if we have h, we should approximately have the relative error. Similarly, if we divide h by a factor of 10, then we should also divide the absolute error by a factor of 10. So let's see what happens. If we see here now, we see that the absolute error, so here's the correct answer. Here is approximately the value of sine at 1 over 2 times h, and this is the actual error of our approximation, at least to a number of digits that we can find useful. You'll notice initially that the error is not exactly approximated by this, but each time the error is reduced by a factor of 10, as expected, at least up until this point. Now something else happens that we have to deal with, and the precision drops off, or the absolute error increases. But at least with confidence we know that the formula is actually a very good approximation of the absolute error. Now in reality, for most problems we don't know what the second derivative is, and consequently we cannot normally calculate the error. Otherwise we wouldn't be doing any of this. So again, the number of digits is approximately increasing by 1 with each step. Now let's try this with something a little bit less familiar, but something that you're going to use later on anyway. The Bessel function, of the second order Bessel function. Now, the derivative of the second order Bessel function is the first order Bessel function minus twice the second order Bessel function over x. Similarly, the second derivative is the 0th order Bessel function plus a combination of the first and second orders. Now, these are actually implemented in MATLAB, so it's not that we have to do anything here. The first term is simply the order. Now, Bessel functions appear anytime you're going to be dealing with electromagnetic fields in cylindrical coordinates. This is where you'll be seeing them again. So again, here we have the correct answer of the derivative. Here we have the approximation of our error based on the Taylor series term, and here is our value of h, our approximation of the derivative, and the error, the absolute error of the derivative. And as again, you can see with each iteration, the error drops by a factor of 10, but at the same time, this formula is actually very well approximated by the error of the Taylor series term. So again, we have confidence that the Taylor series error we determined is actually correct. Now, up until now, we saw that we could actually use h is equal to 10 to the negative 8 as a good initial approximation to the derivative. And it appears to work at least for these two cases. Unfortunately, it may not work for all cases. So we cannot just rely on picking one fixed value of h. It really has to do with the derivative. So this is not always the best approximation, and it may not give us sufficient accuracy if we use this fixed value of h. Now, the real reason is we don't actually understand why the approximation is breaking down. Once we see that, then we can see what we can do to avoid it. Now, suppose we want 10 digits of accuracy in our answer. So again, if h is equal to 0.01, what do we have to do? Well, to get 10 digits of accuracy in this calculation, we need 12 digits of accuracy in both the calculation of sine of 1 and sine of sine of 1.01. So this is sine of 1.01, this is sine of 1. In order to subtract them to get 10 digits of accuracy here, we actually need 12 digits of accuracy in both of the calculations of these two values. Why? Because the first two values are equal and they canceled each other out. Consequently, the accuracy comes from everything from the third decimal place on. Now, if we wanted h is equal to 0.000001, and we wanted 10 digits of accuracy, we would actually need to calculate both of these to 15 digits of accuracy. Why? Once again, notice that the correct answer comes now in the 6th decimal place. And again, we need sufficient digits so that the terms that are the same, the terms that get cancelled, because these two numbers are so close to each other, all the accuracy in our answer is only here in the 5th, 6th digit and beyond. So ultimately we need 15 digits of precision. If you actually wanted to use h is equal to 10 to the negative 12, you'd essentially need 22 digits of precision now. Why? Because again, when you're subtracting these two values, 1 plus h, sign at 1 plus h and sign at 1, notice that the first significant 12 digits are the same, and only after the 12th digit does the subtraction of the first number from the second number from the first give you a non-zero entry. And again, we notice here that this is in fact the derivative once we divide by 10 to the negative 12. Unfortunately, MATLAB, as we saw last week, uses double precision floating point approximations, or floating point numbers, and they use 16 digits, or at least approximately 16 decimal digits of approximation, and so we would not actually be able to calculate all 22 digits. We would essentially end up stopping right about there. So our answer would only be these last 3 digits here. So essentially, our approximation, once we divide by 10 to the negative 12, would be 0.5400000. So we'd lose the accuracy we have here because we have restricted precision in the calculation of both sign at 1 plus h and sign at 1. So this is the problem with the double precision floating point representation. It has finite precision. So that gives us our inaccurate answer. Now, this is not entirely true because MATLAB is really using base 2. We're discussing an example with base 10, but essentially the argument is analogous. It is faithful. We can do this with a binary representation. Use format hex. If you have format hex on, then you see the hexadecimal representation of the double. Now, what does this double mean? You'll recall from last week, the first 3 hexadecimal characters give you the sign bit and the exponent. The balance is the mantissa with an implied leading 1 decimal, or 1 point. So we have 1 point, the mantissa, the exponent minus the bias. Well, that exponent minus that bias is just 2 to the negative 1. So once again, we have that term here. Well, 2 to the negative 1, base 2 just moves decimal place 1 to the left. And so this is cos of 1. If you doubt this, you can actually calculate it yourself. What are these bits here? This is 1/2. This next one is 1 over 32, 1 over 128, 1 over 1,000, 1024, 1 over 4,096, and so on and so forth. You can add up all of those terms, and when you add up all of those terms, yes, you see that that approximation is actually quite close to cos of 1. And if you add the rest of these terms, then you would get the rest of the digits that you see here. If you do it in hex, you will see that the first few hexadecimal numbers are now exact. Everything else is 0 if you only add up those terms. So now, let's look at the approximation of sine, the derivative at sine at 1, the derivative of sine at 1, and notice what happens. With each single iteration, at some point we get 1 more bit of accuracy. However, we also lose 1 bit due to subtractive cancellation. So notice that when n is equal to 26, basically h is equal to 2 to the negative 26, you will see that these two numbers essentially meet. Here, these numbers are accurate. The numbers after this point are inaccurate. They're all 0 over here. If we keep on using smaller and smaller values of h, notice that subtractive cancellation takes over. So this, as I've already used, is the term subtractive cancellation. Colloquial, it's also sometimes referred to as catastrophic cancellation, simply because it causes such issues numerically in actual simulations and approximations. So ignoring the effect of subtractive cancellation is one of the most significant factors affecting numerical approximations. So as a consequence, unlike calculus, where we can make h arbitrarily small in the limit, with double precision floating point numbers, we cannot. So we need different solutions. We need either a better formula or a different approach. Well, we're actually going to see both. Now, where does your formula come from first year? Well, let's say we have the 2 points, x and x plus h. Let's find the line, the interpolating straight line that passes through those 2 points. Notice that we have the formula that you learned in first year. Rise over run, that gives us our formula. Now, let's, instead of using an interpolating line, let's use an interpolating quadratic that passes through these 3 points. Now, if I pass an interpolating quadratic through those 3 points, notice that in this interval, the interpolating quadratic hugs the function quite closely. If we find the slope of the interpolating quadratic at this point, well, you would think that it is actually also a good approximation to the slope of the actual function. In fact, if we look at the two, here it is more reasonable that the slope of the interpolating quadratic is going to be close to the actual derivative at that point when compared to the slope of that line that only interpolates these 2 points. So what is that formula? Well, the formula happens to be, if you calculate it out, u at x plus h minus u at x minus h over 2h. Now, as one additional bonus, since we have an interpolating quadratic does also have a second derivative. It's the coefficient of the x squared term. In this case, the coefficient of the x squared term is this formula here. So therefore, not only do we have an approximation of the derivative at this point, but we also have an approximation of the second derivative here. Now, for those of you who care, you can actually do this in Maple symbolically. You can find the interpolating quadratic that passes through those points. You can differentiate it. You can then evaluate that derivative at the point, simplify it, and you get the formula that we saw, u at x plus h minus u at x minus h all over 2h. You can differentiate again. That gives you the concavity of the interpolating polynomial, and that gives us the formula u at x plus h minus twice u at x plus u at x minus h all over h squared. So we have two approximations, now one of the derivative and one of the second derivative. Are these better than the previous approximation? And if so, how much better? Well, once again, we're going to use Taylor's series. Except notice now that our formula uses u at x plus h and u at x minus h. So let's use both of these. And here, xi plus is on this interval, xi minus is on the other interval. Now, what can we do here? Well, our actual formula for the derivative is u at x plus h minus u at x minus h. So let's subtract the first equation from the second. This minus this gives that term. These two terms cancel out. This gives us twice the derivative times h. These two terms cancel out, and with a third order, now we have a third order error. So that's simply equal to twice the derivative plus 1/6 times h cubed. Okay, we have an h cubed there. Let's divide both sides by h. Dividing both of these sides, solving first for the derivative, and then dividing both sides by 2h. Once again, we see that we get the formula. The derivative is equal to the formula we found minus a 12th times this linear combination times h squared. So what happened here? Now the error is h squared. That means that if we reduce h by a half, the error gets multiplied by h over 2 all squared, or it will be reduced by a quarter. If we reduce h by 10, we will reduce the error by a factor of 100. So again, having h causes the error to go down by a factor of 4. Reducing h by a factor of 10 causes it to go down by a factor of 100. Let's do the same thing. Let's use a fourth order Taylor series approximation for each of those points, however. And in the second derivative formula, we have a sum of these two values, so let's add these two. If we add these two, again, we get 2u of x, good, that's exactly what we wanted. The derivatives cancel, good. The second derivatives actually add up to the second derivative times h squared, so half plus a half is 1. Third derivative cancels, and then we have some term with respect to the fourth derivative times h to the 4. So once again, simplifying it, notice that we have the second derivative times h squared. Let's solve for this expression for the second derivative times h squared, divides both sides by h squared. Notice once again we have the formula we found plus an error term, and that error term is identical in the sense that it has an h squared term there. So now once again, with this approximation, divide h by half, the error drops by a factor of 2, 4. Divide h by 10, the error drops by a factor of 100. So again, we seem to have better approximations of the derivative than we had previously, and the second derivative. Now we're going to actually see that this works by approximating the second derivative of u of x is equal to x cubed minus e to the negative 0.5 times x. Now, if you want to know the correct values of the first and second derivatives, you can use Maple. It will give it correctly to you to 17 decimal digits. Why? Because Maple actually allows you to define how many digits of precision you want. It's consequently slower than MATLAB, but if you actually want to calculate both of these to 100 digits, not that if you're an engineer you should probably don't want to do that, but nevertheless, if you just wanted to for fun, you could actually calculate both of these to 100 digits of accuracy. So, using these formulas, notice what happens. Our approximation slowly gets better and better. The error drops by a factor. With the formula from first year, the error drops by a factor of 10 with each step. H gets smaller by a factor of 10. The error gets smaller by a factor of 10. With the other approximation of the derivative, notice what happens. Again, we get more and more accurate, but with each step the error drops by a factor of 100. Now, the most correct answer is here when we use 10 to the negative 5, and the error is on the order of 10 to the negative 12. Here, the error is found when h is equal to 10 to the negative 8, and the error is now significantly larger. It's on the order of 6 times 10 to the negative 9. So, better approximation, smaller value of h. With the approximation of the second derivative, again, error appears to be dropping by a factor of 10. The best approximation is 1.1882 times 10 to the negative 8. Not as good, but again, you're adding and subtracting more terms. So let's give these approximations some names. This is the first order forward divided difference formula. Why forward? Because we're going forward in x. This is the centered divided difference formula, and this is the second order centered divided difference formula approximating the derivative. All right. Now, suppose you don't actually have access to both x plus h and x minus h, and usually this is when you're dealing with respect to time. So, if you're dealing with respect to time, very seldomly can you actually discuss what's happening in the future. You can only refer to past events. So instead of using t and t plus delta t, we would use t minus delta t, and this would give a slightly different formula. This is the backwards divided difference formula, and as you can guess, this will also be first order. However, there's a different way we could do it. Instead of finding an interpolating line between these 2 points, let's take 3 points back in time, t minus delta t, and t minus twice delta t. Let's find the interpolating quadratic that passes through those points, differentiate it at this point, evaluate the derivative at that point, and we actually get another approximation. Now, those are the two Taylor series for t minus delta t and u at t minus twice delta t. Notice that there's a 2 delta t here and a 2 delta t all cubed here. We can factor out those terms, the constant coefficients, so there's a factor of 4 coming out of there, a factor of 8 coming out of there. And notice that we have the second derivative here. Now, we're looking for the derivative, so what we really want to do is, considering these two formulas, let's take a look at these two terms. Let's multiply this first formula by 4, and that gives this term equal, these two terms would then be equal. So multiplying this formula by 4, these terms are now equal, they cancel out, and notice what happens in addition. We have 4 times that term minus that equals this term here. There's the derivative times delta t, it's actually twice delta t, and now the error term is over here. And the error term is delta t cubed. Dividing both sides by delta t, isolating that term, essentially you get a different formula that uses now u at t minus delta t, and u at t minus twice delta t, plus an error term that is order delta t squared. If we were dealing in x and h, it would be x or this would be h squared. Now, here we have the formula, the second order backwards divided difference approximation. Here we have the second order centered divided difference approximation. Notice that the coefficient out front is slightly larger. Almost. Now, wait a second. We have a 2 here minus. Here we have a sum of 2 values. So, is it actually a factor of 4 worse? Or is it in fact not that bad? It's actually only worse by a factor of a half. So that's actually not that bad. So what are you going to do? First of all, you're going to write 4 functions. You're going to write your function that takes as an argument u, which is a function handle, a point x, and a value h. This function will return the first year approximation of the derivative. Then you will use the centered divided difference formula, the second derivative centered divided difference formula, and the backwards second order divided difference approximation. So implement all of these, and yes, all of these functions are one line. So why are we doing this? Well, we're going to get a little bit better. But nevertheless, how these work, you should be able to enter these 2 values and you'll get these approximations of the derivative. Again, with the centered divided difference formula, we get slightly better answers. We can also calculate the second derivative using the centered divided difference formula, and we can also use the second order backwards divided difference formula. All of these your functions should return exactly these values. Now, that was finding a better formula. Let's also look at a better approach. So now we have better formulas, let's see if we can do even better. the first thing you think of is finding interpolating polynomials of more points. Say, find the interpolating polynomial between 5 points. Unfortunately, there are issues with such approximations that are beyond the scope of this course. So instead we will look at Richardson extrapolation, which oddly enough is not going to be subject to the subtractive cancellation that we get if we use more and more interpolating points. Now, if we have that the derivative is approximated by this, you can actually calculate a full Taylor series approximation. What are the error terms of this approximation? So essentially, if you took the entire Taylor series to an arbitrary number of terms, solved for the derivative, you would get this form, and now you would get the error terms. Notice that the error terms are h squared, h to the fourth, h to the sixth, and h to the eighth. Every second error term would actually be cancelled out. The second derivative is almost identical. Notice that the error term for our approximation is h squared, but if we look at the higher order Taylor series approximations again, it's h to the fourth, h to the sixth, h to the eighth. Okay, so what? Well, let's see if we can exploit this. So first of all, let's simplify how we write our approximation. D sub c takes a function, a point, and a very small value, h, and returns the derivative using the centered divided difference approximation. So this is your DC formula. Therefore, the derivative is our formula plus an error term. And that error term goes on. Now, let's see if we can exploit this correctly. Here is our approximation. And now, let's use the same centered divided difference approximation, but let's pass the value of h over 2. That means that we're going to get a better approximation. Why? Because here, this error term is now reduced by a factor of 4. This error term is reduced by a factor of 16, and so on and so forth. So the error is being reduced by approximately a factor of 4. Expanding this out, we get those terms. And now let's see what happens. These two terms are the same except for the coefficients. This is 4 times larger than that. So let's take this equation and we'll subtract this equation from 4 times this equation. Notice what happens. 4 times this minus this is again 4 times dc with a factor of h over 2 minus this term. 4 times this minus that cancels out. So all we're left with is 4 times this minus that. That's a coefficient times the fifth derivative times h to the fourth. There's an h to the fourth there, not h squared. Let's solve for the derivative, because now we have 4 times the derivative minus the derivative, that's 3 times the derivative. Let's divide both sides by 3. So now, here we have, given 2 approximations, we can take a linear combination of those 2 approximations, and that gives us an approximation that has an even smaller error. Cool. That's an order h to the fourth error. So now, if we take both of these, reduce both of these by a half, then the error of this approximation will drop not by a factor of 4, but by a factor of 16. So let's try it. Using h is equal to 0.01, there is our coarse approximation using h is equal to 0.01. This uses h is equal to 0.005, or a half of this value of h. Let's take 4 times that approximation, subtract off that approximation, divide by 3. Those are the 2 values. And now, notice what happens. Here we have 1, 2, 3, and then that's it. We get more approximation here. So in either case, here we have 3 digits of approximation, There we have 5 digits of approximation. Neither is that impressive. There's the actual value. However, if I take 4 times the better answer, subtract off the worst answer, divide by 3, notice that we now have 2, 4, 6, 8, 10. 10 digits of approximation. We took one answer that had 3 digits of approximation, one answer that had 5 digits of accuracy. We took a linear combination of them, and we got 10 digits of accuracy. And all we did was take a linear combination. That's it. That is how it works. What's really cool is if now we divide h by half, and so use h is equal to 0.05 here, and h is equal to 0.025 there, then we would reduce the error now by a factor of 1 over 64. Or we'd reduce the error by a factor of 64. So once again, notice that if we calculate with a smaller value of h by a factor of 2, notice that we get a significant number of digits that are accurate. How small must h actually be? Well, given this error term, solving this for the desired error, we get a value of h is equal to 0.000224. Plugging that in, if we wanted to use our base formula, our center divided difference formula, to get the same accuracy that we got here using values of h such as 0.005 and 0.0025, we would actually require a value of h as small as 7 times 10 to the negative 12. This uses significantly more subtractive cancellation, and in fact, this is beyond the point of subtractive cancellation. So we could not get that accurate an answer just using the formula. So we could repeat this again. In fact, we can always do this. If we ever have something of the form, something is approximated by an approximation depending on h, where the error term is some constant times h raised to the power n plus lower order terms of h. Now, if we divide h by 2, now this error term is divided by 1 over 2 to the n, because, again, the 1 over 2 to the n factors out. The lower order terms really don't matter. If we multiply this by 2 to the n and subtract off that term, notice that we cancel both of these terms out, and all we're left with are the lower order terms in the error. Solving this means that if we take 2 to the n times this approximation minus the coarser approximation, we lose the h to the n error, and we're left with lower order terms. And again, it's just a weighted average of the two. Now, is that formula subject to subtractive cancellation? Well, actually it isn't. Can you think of why? For subtractive cancellation, we had to subtract two values that were approximately equal. So sin at 1 and sin at 1.0001. However, both of these are approximating the same value. This might be 8 times the value. So 8 times something minus something is not going to be very close. Consequently, we do not have this term affected by subtractive cancellation. All right, so how can we use this to find better and better approximations of the derivative? Well, suppose that we have our initial approximations of the derivative using h over 2, h over 2 to the squared, h over 2 cubed, and so on and so forth, each time dividing h by a factor of 2. If the highest order error is h squared, then that means that we can reduce the error by taking 4 times the better approximation, subtracting off the worst approximation, and dividing the result by 3. This works in each of these cases. 4 times the better approximation, subtract off the worst approximation, divide by 3. 4 times the better approximation, subtract off the worst approximation, divide by 3, and so on and so forth. Now, for the center divide difference formula, all of these are dropping now by a factor of h to the 4th. So if they're dropping by a factor of h to the 4th, that's 1 over 16. So the error here is 1/16 the error here, approximately. So we could take 16 times this, minus that, divide by 15, and now you get an even better approximation. So again, 16 times the better approximation, subtract off the worst approximation, and divide by 15. Even down here, 16 times the better approximation minus the worst approximation, divide by 15, gives you a better approximation. We can repeat the problem again with, again, the centered divide difference formula. The next error term is h to the 6th. So once again, we can get rid of that by taking this value here, multiplying it by 2 to the 6th, or 64, subtract off the less good approximation, and divide by 63. Ultimately, we can do the same thing here again. Now the error term is h to the 8. So now we could actually take 256 times this value, subtract off that value, divide by 255. We probably will not be getting this far. However, notice that this essentially creates a matrix of entries. So we could actually solve this quite easily. Calculate this value using h over 2, h divided by 2. Evaluate this value and see how close these two are. Now, divide h by 2 again. Calculate 4 times this, subtract off that, divide by 3 to give you this. Subtract 16 times this, minus this, divide by 15 gives you this value. Now you have a better approximation. Compare these two and determine whether or not they are sufficiently close. If they're sufficiently close, you can end. So you will therefore be required to, for the centered divide difference formula, both second order terms for the first and second derivatives, you will implement Richardson 2-2. 2-2 indicates that the first error term is h squared, and each subsequent error term is 2 beyond that, h to the 4th, h to the 6th, and so on. What are you going to do? You're going to create an n sub max matrix, n sub max plus 1 by n sub max plus 1 matrix, all of zeros. You will then calculate the first entry using the past value of h with whatever derivative you're past, be it centered first order, the second order centered divide difference approximation, or of the first derivative, or the second order centered divide difference approximation of the second derivative. Both of them can be passed as the first argument. That's why you are writing them. Next, we're going to have a loop. A variable I iterates from 1 to n max. We're going to calculate the next value down along the first column using h divided by 2 to the I. We will then loop. J goes from 1 to I, and we just fill in up until the diagonal, each time using a larger power, 4, then 16, 64, and so on. Finally, if the entry that's just been added to the diagonal is very close within epsilon sub abs of the previous entry on the diagonal, then we finish. We return the most accurate answer. Otherwise, we keep on looping. If the loop finishes, we reach n sub max and we haven't terminated yet, then we throw an exception. And you have to create the appropriate exception, which you learned last week. So here are some examples that you can look at. Again, here we passed the divided difference approximation using the centered formula, second order. And here are some values. You can try it, make sure you get the same answer. Cos of 1, sine of 1, you can see that we are accurate to almost all digits. We are only inaccurate in the last digit in both of these cases. Same thing here. H is equal to 10 to the negative 12. Our approximation using Richardson extrapolation on the derivative gives us everything up until the last digit. Now, if we try using the second derivative, it doesn't work as well. Sometimes we get an approximation, but if we use h as small as 10 to the negative 12, sometimes it simply doesn't converge. So you might have to use a smaller value of h, but notice, once again, we get still get a significant number of digits of accuracy. Now, the Taylor series for the backwards divide difference formula is not as clean as it is for the center divide difference formula. Here, yes, the first term here is delta t squared. Again, here we're usually interested in time, and so now we're going to consider the derivative with respect to t. Delta t squared, delta t all cubed. So notice that squared, cubed, raised to the power 4, raised to the power 5. So now the error terms are not dropping off h squared, h to the 4th, h to the 6th, but now h squared, h cubed, h to the 4th, h to the 5th, h to the 6th. So you're going to have to create a different function that works for Richardson extrapolation with respect to h to the 6th. This pattern with the backwards divide difference approximation. Now, what happens if we're using the wrong Richardson extrapolation? Actually, it's not that bad. Because we're just combining linear combinations, it just mixes up the error. It doesn't increase the error. So putting an approximation through a Richardson extrapolation that is wrong simply gives us an answer that is on the same order of badness. So that in the lab you will actually also implement a function for Richardson 2, 1. Starts with order h squared, then h cubed. After that it increases by 1. So in this topic, in this lab, we've seen the effects of subtractive cancellation on the derivative. We've found better approximations using center divide difference formulas. We also saw the backwards divide difference formulas. We determined the error terms using Newton's method, using Taylor series, and then we saw also how Taylor series can give us Richardson extrapolation to reduce the error even further. Richardson extrapolation is used here, but it's also used in many other formulas. For example, Romberg integration for approximating an integral from a to b. So, good luck with your lab, and cheers. Have a good day.